will hold a lot of relevance as we start to market our Chroma White product, and we're going to introduce new metrics which help set Chroma White apart from the other LED products available today. So we will cover color rendering and the different ways that it's measured, color shift and things that will influence that over time, and color consistency between light sources and fixtures. And then we'll put that all into context by talking about Chroma White. So what do we actually mean by color quality? Well, in essence, we're trying to tie it back to a reference point of natural daylight. That's what we evolved to thrive in. This is about our vision and also about our health as well, because our eyes don't just process light vision, but also to entrain our circadian rhythm, that being the topic of a separate presentation. But providing good quality light is essential in order to enhance our well-being and our human performance. And it also is about providing light that renders objects as close as possible to daylight, and that's what we're intending to do with the perfect artificial light source. So why do we want to assess colour quality? Well, we're looking at how faithfully we can represent light in terms of natural daylight, how well it renders the colours as natural daylight would, how attractive things look when they're illuminated by a light source. Do they look vivid and saturated? Can you actually tell the difference in colour between one object and another? And then we'll add in all the non-visual responses that we talked about earlier. In monetary terms, getting this right could achieve greater sales revenue by making a product look more attractive, by having the well saturated and being able to make it look very appealing. Might result in greater sales. You might make better medical diagnosis, and also you can evoke some emotional responses as well. Colour rendering is actually about light sources, though. This is a measure of the ability of a light source to reproduce colours faithfully compared with an ideal reference source, typically natural light, but it could also be a black body radiator of the same correlated colour temperature. So how can we actually communicate that? Well, it does depend upon the context, but you need to look at what it is we're trying to evaluate. Are you trying to look at, does an object appear natural under the artificial light source? Are you trying to differentiate subtle shades and differences in colour? Or are you trying to make something look vivid underneath this artificial light source? And what we can say is there is no single metric that can answer all of these questions. But typically, there are three ways that we are commonplace at the moment, and one that is becoming more commonplace. So colour rendering index is something typically used within the lighting industry to show how well a light source renders colour. There are a number of extra features that we're going to go into about colour rendering index shortly. It doesn't really work well for an LED product. Gamut area index is another way of comparing light sources typically to daylight, and that's something that we are going to use more in our materials going forward, because it's a good way of showing how great Chroma White is. And full spectrum index is another way that we will demonstrate shortly, and that has some other uses. So colour rendering index, historically used 8 swatches, typically now uses 14, or in some cases 15 with an extra skin tone swatch, and this is an index used to rate how well the light source renders colours, but it's compared to a black body reference of the same CCT, so we've got that comparison. Gamut area index uses the same 8 test reference swatches, but it's a measure based upon volume in the colour space. We'll show that in a minute to give you a bit more detail. And then full spectrum index, mathematical measure of how much of the light source's spectrum deviates from an equal energy spectrum. So it's about how much energy you have in different parts of the spectrum. So they're all very, very different measures, and they tell you quite different things. And in different applications, a combination of 1, 2, or 3 of them might be relevant. So we all know that incandescent lamps have the highest possible CRI value of 100 using the typical CRI approach. But did you know that it scores poorly on full spectrum index and, in fact, gamma area index? The reason it scores poorly on full spectrum index is because it's quite deficient in the short wavelength range. So depending on the application, you might choose different metrics. CRI absolutely fine for things like residential applications, but gamma area index is much more appropriate for the intention of lighting in a retail application. It's a good plan to try and use at least 2 metrics, and that gives you considerably more information and a BRE study, which we have copies of, should you wish to provide it to your specifiers, will show how 2 metrics as a combination was a much stronger indicator of human responses to products lit by different light sources. You are going to start seeing manufacturers' data provided with not just CRI, but typically with GAI data and potentially CQS, which we'll come on to in a minute as well, and FSI. Zacato are providing a lot of information in this form. If you wanted to have a look at their website, we are going to start doing it specifically for the Chroma White products as we move forward. So color rendering index, this is about the light source's ability to reproduce color faithfully in comparison with a reference source. The higher the number, the better, 100 being the best, which is natural daylight and incandescent light sources. This is something you're probably very familiar with and specifiers very familiar with. Let's break it down a little bit further. So what is color rendering index? It used to be that color rendering index took 8 swatches, 8 reference swatches, and looked at, in comparison with a reference light source, how true to the reference light source these colors were rendered in the swatches. Unfortunately, that doesn't do well for LED, to show how well LEDs render color. So we also have these extra swatches now. So we now have up to R14, which includes the saturated colors. There is a 15th swatch as well, which looks at skin tone, and that's obviously very important for specific applications such as makeup and medical. So you have to ask the question when somebody gives an average of these, the RA, are they averaging just the first 8, which typically is the approach, or is it 14, or is it 15? Most photon star data is actually R8 because that's what the LED chip data sheet gives us. We can provide you R14, we can provide you R15, but if we don't state, then it is R8. And that would be the case typically with most manufacturers. With our Chroma White products, we break it down into each individual swatch so the specifier can make the decision for themselves which average they'd like to use. So CRI doesn't work well with LEDs, the problem being where under an individual swatch it might perform poorly, so you've got issues with the averaging. But most LED products, of course, have an RA of 80 or more if you are doing an average of the first 8. But common problems with poor performance in saturated colors, specifically the reds, can drive that number down a little. Gamma area index, this is another alternative, and this is one we're going to focus a lot of effort on. There will be another presentation, it's just an introduction today, but this shows Chroma White off at its best. So this is, this graph here shows how well different products perform. These are the LED products, we'll some others shortly, but you can see this blue one here, that's daylight. Obviously we want to be as close to daylight as possible. And this is a ColourMix LED product. It's incredibly close to daylight. Whereas if you looked at a warm white LED, you can see we're not doing quite as well there as daylight. So this really shows chroma white off at its best. And in fact, most RGB LED products perform well when measured in this way. So it uses the same 8 swatches, which is why you get a polygon, and then these are plotted in the colour space. And you can see here that whilst our lovely incandescent that did so well in the CRI measure, it doesn't do quite so well when we look at the GAI score. Something certainly worth pointing out to specifiers working in retail and medical applications. So a light source with good CRI and a good GAI score would have good colour fidelity and good colour vividness. This is an ideal thing if you're looking to sell products, as in meat, vegetables, or dresses, or anything like that. So a low GAI score, it basically is not going to render those saturated colours well. And you also don't want something with an overly large GAI because the colours may appear oversaturated and slightly unnatural. So ColourMix LED solutions perform best when you use this metric compared to a traditional lamp. Full spectrum index, just going to kind of very lightly touch on this one, but we will produce the full spectrum index data for chroma white should anybody want that. And I'll leave you to read the slide there. That's just the key data for today. So in summary, high CRI does make colours appear very, very natural. We want a low full spectrum index to give you good discrimination between colour variations. A large gamut area index will give some very saturated colours. And so if you use a combination of these metrics, depending on your application, you're going to be able to establish the right light source for that application. So we're going to be supplying CRI information for chroma white broken down into the individual 15 swatches. We'll also provide full spectrum index data and GAI data as well. And what you will find is that chroma white actually performs well across all 3 of these metrics. Just one other item to note about maintained colour rendering index. All of our products are designed that at 6,000 hours or 25% of the rated life, we expect our CRI value to be within 3 points of the original value. It's actually in the subtext of our data sheet, but it's part of the LILG guide to how to specify LEDs. So now on to colour shift. Or white light is measured in Kelvin, degrees Kelvin. This is best comparable to natural daylight. So at sunrise, our CCT would be about 1800 Kelvin, really quite red. So let me just mark this on the, there we go, right down at this end. And as the sun rises higher in the sky, it's refraction that causes the different colours of light. So as we come, there we go. Depending on where you are in the globe, the midday daylight could be between 6 and 10,000 Kelvin. And also the clouds and weather can have an effect as well, but it does vary depending on where you are and the weather conditions. However, this is also white light based on a black body radiator, so something hot and glowing, and that is where the degrees Kelvin comes into it. So something that is actually physically not very hot is a warm white, slightly contradictory there, but that's the term warm being redder, and something that is in fact has a very, very high temperature, 6,000 Kelvin, glows whiter. And hence the high CCT being a very cool white. So, how much colour shift can you actually perceive? Might not be able to perceive a great change in colour, but certainly if fixtures adjacent to each other have a different CCT, typically people can perceive a colour shift of 2 to 4 macadam ellipses. We'll come into some more detail on that shortly. But there are 3 main factors that can influence colour shift in an LED luminaire. The first thing is heat. The LEDs themselves, if you look at the data sheet for an actual LED, you'll see that you get different performance at different junction temperatures. It can vary quite a bit, so it's important that when we state any performance data at all, we say at the temperature that we expect it to perform. We also state the operating current as well, so dimming by use of current and dimming itself will also change the CCT, and of course time. It is likely to shift in colour as well, but not necessarily in a way that you're going to expect, because this combination of the 3. So your eye is actually more sensitive at the warm end of the visible spectrum, so you would notice a very, very subtle colour shift on a warmer CCT than you would perhaps in the cooler. So, and that of course is where the more desirable product sits. So colour consistency is essential with these higher quality products. Over a period of time, as LEDs age, the forward voltage required to switch the diode increases just very, very subtly, and this can also cause a tiny shift in CCT. How do we get around that? Well, we buy very good quality LEDs, and we will test those to ensure they will perform it as expected. We're looking for an extremely tight forward voltage bin, so that we don't notice any colour shift over time, or at least we minimise the colour shift over time. So on to colour consistency. So what's colour? That's the first thing, and how do we differentiate one colour from another? So in order to define a particular colour, you need the amount of red, green and blue to specify that colour precisely. Now, many years ago, a scientist, David McAdam, set up an experiment in which each trained observer would observe different colours at a fixed illuminance. And this was to confirm his suspicions that colour difference could be measured using a metric in a chromatity space, and that is the diagram shown here. So what is a macadam ellipse? So this refers to the region on the chromatity diagram, just here, which contains all the colours that you can't actually distinguish the difference. Now, obviously, this is quite subjective. Everybody is slightly different, and we're very aware when we're looking at chroma white that certain colleagues can distinguish colours better than the other. But effectively, within one ellipse, you shouldn't be able to notice any difference from one colour to another. So over a period of time, the colour of a light source obviously will vary, as we talked about earlier, with the colour shift. So we need to make sure that any products are within the expected tolerance so that people cannot tell the difference between one luminaire and another. And the Photon Star products typically are shipped within a 2-step macadam ellipse, so most people cannot tell the difference at that point. However, there are different standards, 1, 2, 3, 4, 5 and 7-step ellipse that are fairly normal in the industry. We also have to look at how that performs over time. So usually at 25% rate of life, typically 6,000 hours, and 6,000 hours as a minimum. and we will categorise how well we expect that to perform over a period of time. You'll be aware on our data sheets, it will say here the size of the macadam ellipse centred on the rated colour target, and we will have initial and maintained. And typically on our current data sheets we say 3, although we're expecting to perform slightly better than that. Bear in mind all the things we talked about earlier that can affect the colour of the lights also over a period of time. So we will say that that's our expectation within a specific temperature over a particular period of time, operating at a specific current. So chroma white. Again, we'll have a longer, more in-depth presentation about this at some other point. But it's because it's a colour mix, colour tunable light source, it has a number of advantages in the various metrics that we talked about earlier, and it offers some solutions that can meet the needs of really demanding applications such as retail and medical and art, in terms of being able to differentiate colour and in terms of offering good saturation and vividness, faithful representation to daylight, but also eliminating some of these problems such as colour shift over time and colour accuracy between one fitting and another. This slide probably just says exactly what I've talked about before, and I'm just going to whip through this a bit quickly. It's our fairly standard presentation that you've already seen. Right, but you're again looking at the colour quality. Chroma white is superior both in terms of CRI and GAI, and potentially in terms of CQS, which we haven't gone into in any detail here today, but is something that we're going to start asking you about, and we'll have a separate presentation on. But one of the main things is to look at over all the 15 swatches, chroma white is expected to perform at a similar level to tungsten halogen, which is considered the superior light source. It also performs very well in these more saturated colours, so particularly the red, which is often a problem. And this gives us an RA of 96, that's as an R8, but it's also over 90 when measured as R14 or R15. But unlike halogen, it's much closer to daylight in terms of gamut area index as well. This large gamut area index is going to offer considerably better saturation. So what we can see is the colours of things illuminated by chroma white are going to look more saturated and more vivid, and also it's going to render it very close to daylight, so it is going to be truer colour as well. So there's your chroma white, the colour swatches for chroma white at different CCGs. It does perform differently at different colour temperatures. And then we're comparing it with our typical LEDs. So this, I believe that top one is a Cree test, and you can see that it doesn't perform very well in the reds. It's a 20. It is actually possible to have negative figures on these as well, but because you're averaging only the first 8, this particular LED product scores quite highly at 85. If you were to do an R15, obviously this wouldn't score very well. And that's it for that presentation. Thank you very much.